Okay, in this video, we are going to have something slightly easier than what we encountered in known distributions. So basically, we will just review a few important definitions which you probably have met before in your statistics or probability course. The first slide is about sum of IID random variables. Somehow we already mentioned the general idea, especially the summation part. Now we want to get the sample mean. Sample mean, denoted by X bar, is the summation of n independent and identical random variables divided by n. So this is how we construct the estimator X bar, okay, sample mean. This is a new random variable, okay? Because all xi's are random variables. We sum up, we have a new random variable. We divide it by a constant, you still have a new random variable. Okay, because all of them are IID, it's very easy to show that the expectation of X bar is mu. By the way, mu is the mean of those xi, and the sigma square is the variance of xi. Okay, the variance of X bar is sigma square over n. This property later on, well, in much later chapter, we will call this unbiased because the mean of this estimator equals the parameter, right? So let's say in general, mu is some parameter, it's a constant, but in real life, we don't know the value of it. So here we have a nice property that the expectation of our estimator equals the parameter we are trying to estimate. So that's why we call this unbiased. And this is also somehow efficient in the sense that if you take n to infinity, the variance goes to 0. That means when the size of your sample increases, the accuracy of your estimator improves. So that is really something we hope to see. So in general, okay, so the sample mean is a nice estimator. We will learn actually a lot more in later chapters about estimators. Then we have the sum of two. Okay, previously we have sum of n and then we divide by n. Here we only do the summation. And if both x and y are discrete random variables taking non-negative integer values, then things become a lot easier. We can actually discuss the values. Start with, here I start with 0 for x. If x is 0, y must be n because the summation is n, right? And then I increase the value of x by 1, then automatically the value of y will go down by 1, right? I go all the way to n, right? I cannot go beyond n because both of them take non-negative values, right? So with this assumption, by the way, this is the assumption we imposed on chapter 1 because we study claim frequency, right? The number of claims. The smallest one is 0, right? So it's reasonable for this chapter. So that's why the computations are actually easier here than the general case, obviously. When you have the continuous case, this is the famous convolution, right? This is something we will need to study. So that's convolution. The general formula is here. Right now, x and y can take negative values. So I need to vary the value, from negative infinity to positive infinity. Here I condition on y. So big Y equals small y, then small x, big X should somehow close to z minus x. Of course, this is not exactly the meaning because we cannot talk about the probability of a continuous random variable equals something. But anyway, it helps us to understand because we are concerned of the summation, right? And if the summation is somehow z, then we need to break one of them to be y, the other one to be z minus y, right? So that's the naive understanding of the convolution formula. In the next section, we introduce a special class which is useful in the next section, in particular in Panya's recursive formula. That means the content of this section is more used for the next one. So here we have a definition. So basically, we call a random variable in the family of AB0 class if its probability function has this recursive formula. So here we have a recursive formula. So we have a recursion down here. Okay. So most of the distributions we have introduced fall under the AB0 class. Okay. This table is nice. It actually summarizes the values of A and B and the initial value of the probability function. So the initial is at 0 for all the 4 distributions we have studied so far. Okay, there's no need to really memorize what A and B's are. Once you are able to write down the probability function, it's rather straightforward. Right? It takes 20 seconds to figure out the A and B. Right? So, for instance, if we have Poisson distribution, my Poisson of x will be e to negative x lambda to the power of x, x factorial. And if I want to go to -1, I can write this as x minus 1 times x. And then x factorial, I can write as x minus 1 factorial times x. So what I have is 0 plus lambda divided by x times the probability of x minus 1. So I know A is 0, B is lambda. A is 0, B is lambda, right? So there's really no need to memorize. Once you are able to write down the probability function, you can figure out A and B. Somehow slightly more difficult is the negative binomial. In that case, you need to know you need to expand the combination number. Okay, so that's the slightly tricky part, but I don't think it's complicated. So I trust you to derive the formula. Let me know, if you have trouble figuring out A and B for negative binomial. From here, we see again that geometric is nothing but negative binomial with R to be 1. So R to be 1, then it is 0, right? When you plug in the R to be 0. And when R is 1, this is indeed theta. So this is another partial confirmation of geometric being negative binomial with R to be equal to 1. So a few remarks. Only the last one is important. Okay. Here we call this AB0. That's because in this definition, the recursive formula starts with 0. Right. On the right-hand side, your x can start from 1. So the first value we have is actually fx0. So the only information we need is the starting value. That's why in this table, I give you the initial value at 0. Okay. Once I know the initial value at 0, I know the values for A and B. I can use this recursive formula to derive to any value I would like to. Right. So that's why it's called AB0 class, because here we need A, we need B, and we need the probability function at 0. Okay. Somehow a related concept is AB1. Okay, everything is the same except here. The starting value is not 1, it's 2. For AB1, I start with the probability function at 1. Okay, but it's, if I know the probability function at 1, I can use this formula to derive the probability functions at 2, 3, all the way to infinity if I want. And then to figure out the probability at 0, I just use 1 minus the summation of the rest, right? So we also just need one condition to figure out the rest, okay? So given x from AB1, somehow, this guy the first value is not part of the family or the part of the recursive formula. And one thing I want to mention is it does not need to be 0. It can be anything between 0 and 1. Okay. So that's why here they only differ by the initial value. Okay. The last one is important. Actually, SOA tested this type of question before. So let's focus on this one. The reasoning is as follows. Okay. Say we want to apply a specific AB0 class distribution to model X. Okay. Somehow we are happy with the general feature of the selected random variable, but we have trouble matching the 0 value. So the value we have from 0, the distribution value does not match exactly what we observe. So we observe something that is way different from the probability function at 0. But after 0, the feature, like the relative shape, indeed fits quite well of the selected AB0 class. So in this case, what we can do is we modify. We modify the 0 value. Okay. In order to do such modification, we follow those steps. In step 1, we select a particular AB0 class which we would like to fit. Okay. After the selection, obviously we know the probability function. Okay. Since 0 is the point that we cannot match, we simply assign 0 value to the observed value. So this is somehow what we observe, okay, which does not equal to the selected AB0 class at 0. Okay, this is the issue we are trying to resolve. So of course, one way is to simply set the 0 value to be what we observe, and then we do modifications on the later on values. The transformation we do is we apply a positive factor. Okay, of course we need to change something, right? Otherwise the summation of all possibilities will not be 1 because we already changed the initial value. Okay, but somehow we want to retain the feature of this AB0 class, which means we want the recursive formula to stay. Okay, the transformation we can apply is then a factor, right? We times by a factor. Then obviously this is C times fx, and because the x random variable comes from the AB0 class, so I know that is b divided by x times by fx x minus 1. Right? So I can move this outside. By our definition, C times fx is the modified. But now I am at x minus 1. So after this modification, we are still at the same recursive formula. I don't change that. The only thing I'd like to change is the initial value, okay? But now the question is, what is this C, right? C has to be special because we want the new summation to be 1, right? So here, this is a modified. I change the value at 0, and for the new one, it is C times the original probability function. And for this, I can write it as 1 minus the initial value, right? So from here, I can figure out, or I can derive the special factor C. It must be in this specific form so that the new probability function summing up to 1, okay? The whole procedure is called the 0 modification distribution. So we modify the AB0 at value 0. So we modify the probability at 0. So that's why it's called 0 modified. And a very special case of 0 modified is 0 truncated. We simply let the probability at 0 to be 0, which means we don't want to see 0 happening. That's maybe what we observe from the reality, zero does not happen in some applications, so we truncate. So that's the meaning of zero truncated. So zero truncated is a special case of zero modified with modification being zero, right? So of course we can try a different modification. Here we have example. So let's use this example. Take a look at the question, and we're going to solve. This is negative binomial. By the way, in this special negative binomial, r equals 1.8, which is not an integer. Okay, it's okay. So although in formulating the negative binomial, my intuition is that I want to know how many failure events before I see the r's success event. In that formulation, r should be a positive integer. But I also mentioned that as long as we figure out the probability function, r does not have to be a positive integer, because we can calculate the combination number for a decimal. Right, so here is exactly 1.8. So the decimal number it's okay. You can use calculator. So this is x is distributed as a negative binomial. What is the recursive formula for the probability function of x? I leave that to you. Okay, so that's the easy part. Now I want to derive a zero modification distribution with new probability at zero. So first we want to know what is the original one. So again, the meaning is I want to see r's success here. It's a little bit weird, 1.8 success. The value is zero, which means I don't want to see any failure. So that is what I want to see. So 0.3 is the probability of success, right? I raise the power to the number of success events I want to see, right? I don't have any failure events. So this you can easily calculate is about 0.1145. Obviously, this is different from 0.6, right? So basically, the rationale is I'm trying to use a negative binomial distribution to fit the data, okay? According to my fit, the probability at zero is a little over 11%. However, what I observe is about 60%. The difference is too huge, right? So I will need to do the modification. I directly set the probability. I directly set the modified probability at zero to be what I observe, okay? But obviously I will need to change all the later on values, right? Because I increased the value by almost 50%. So the rest together will shrink by about 50%. So the reason to do that is to keep the same recursive formula. Then we have to, okay, the modification minus the original one. So I get my C is about 0.4517. Okay, so this is my C. Then I want to know the mean and variance of the new modified random variable. Let's call it xm. So to calculate this, I separate this as zero and non-zero. When the value is zero, the probability is 0.6, although I don't care. From 1 to infinity. So here is x times c of xx, right? Because this is the new probability density or probability function, right? C times the original one. So it's actually c factoring out. Right? If you want, you can start with zero. It doesn't change anything. So this is c times the original one. So you basically change the mean by a factor of c. So we know the c, and we know this is r times 1 minus theta divided by theta. right? 1 minus theta over theta is the mean of a geometric distribution, right? And we know negative binomial basically summing them up. So this is R times it, okay? So you can quickly get the result. Variance is slightly more complicated, okay? My preference is to consider the square of the modified random variable, okay? So the reason we will see, okay? So the reason is because when I consider directly the square, it's easier to understand. So 0, I don't need to care, because 0 times anything is still 0. So as you can see, this keeps the same proportion as to the original squared term. Of course, we don't directly know the expectation of x squared, but luckily we know the expectation of x squared equals the variance plus the square of mean, right? And we know this, okay? So in fact, the variance is r times 1 minus theta divided by theta squared. So, you have additional theta at the denominator. And then we have 1 minus theta divided by theta. This entire term has to be squared. So we know C from here, we know R, we know theta, so this can be easily calculated, right? So once I know the square, of course, I know the variance, right? So that's usually how I solve it. If you want to directly apply the definition, it's rather complicated, right? So I think this is a nice strategy for working out the variance in this particular case. I will stop here for this video. In the next video, we will study the final section of this chapter.